Okay, it should be running.
I think we'll wait a couple of more minutes before we start. Okay, we'll wait 2 more minutes and then we'll begin. So people are slowly joining the stream on the YouTube. Okay. Let's start. Welcome to ChemTalks, the online conference where scientists present advancements of their researches and give talks on their cutting-edge scientific themes. Today, our speaker is Dr. Arnab Majumdar from Terramera, which is a clean tech leader from Vancouver. It is focused on AI and science, and they are trying to revolutionize the technologies that transform how we grow food and solve other world-scale challenges. Let me briefly introduce Dr. Majumdar. He received his bachelor in physics at Sant Xavier College, Calcutta in 2010 and completed his master's program there in 2 years with a focus on computational chemistry, MD simulations, and condensed matter physics. Then he moved to the University of Saskatchewan and completed his PhD in 2018 in theoretical condensed matter physics under supervision of Professor Tse and Professor Yao. After completing PhD, Arnab continued his academic career and worked as postdoc in Uppsala University and the University of Montreal in Ahuja and Coty groups, respectively, dealing with neural networks, ML, DFT calculations, and focused on the prediction of the existence and properties of materials at extreme conditions. Dr. Majumdar, thank you very much for coming. It's a pleasure to host your talk, and the virtual scene is yours now.
Okay, thank you very much. Good morning to all of you. It's actually quite early in the morning here in Vancouver. Thanks for the very kind introduction as well. So as you can see that the topic of my presentation today is reduction of thermal conductivity in monolayers owing to alternative atomic configuration and how this alternate atomic configuration in 2D chalcogenides improves the thermoelectric efficiency of materials. But before I go into the details, Igor has already given a very nice introduction. So just to add on to it a little more, so during my PhD and my first postdoc in Sweden, I focused mostly on high pressure physics, high pressure phase transition, superconductivity, etc. Towards the end of my postdoc in Sweden and also during my postdoc in Montreal, I transitioned into calculating thermal properties and thermoelectric properties of materials. Last year, I transitioned from academics to industry, and I currently work for Terramera, which is located in Vancouver, Canada as well. The work that I do currently has nothing to do with the thermal conductivity that I'll be showing today, but it's still a side research that I keep doing with my collaborators and colleagues from time to time. Okay, so before I talk about my own research and my results, it's imperative that I give a little bit of an overview of what I'll be talking about. So if you look at the little diagram, you'll see that in most of the avenues where energy is used, 2/3 of the energy, that is 66%, is actually wasted, and only 1/3 is used up. So this 2/3 of energy which is wasted, a lot of it comes out as loss in heat. So the idea was that, can we reuse this lost heat in some way? Can we convert it into some other form of energy which we can use again? If we could, then we would be able to solve a lot of the energy issues of the world, number one. Number two, that would eventually even lead to a better sustainable lifestyle. This particular effect was called Thermoelectric Effect, where we convert heat into electrical energy. Okay, so a little more about Thermoelectric Effect. Many of us probably remember studying this in high school, that the two effects which constitute the Thermoelectric Effect are the Seebeck effect and the Peltier effect. Now, with regards to what we will be discussing today, we will be needing the Seebeck effect more, and I've described that in the next slide. Right. Let's start with the diagram to the right. So you'll see that there is a closed circuit, and the closed circuit is actually made up of two different metals. One is material A, which is in red, and then you have material B, which is in dark blue, and they are connected at two different junctions. Now, at these two different junctions, when there's a temperature difference, it was seen that there's a current which flows through the circuit. That means a voltage has been developed. This exactly is the Seebeck effect. How do we quantify it? You can look at the equation to the left. We see that S is equal to delta V over delta T, where S is the Seebeck coefficient, delta V is the voltage difference, and delta T is the temperature gradient. Now, we have to keep this in mind, that we'll need this Seebeck effect and the Seebeck coefficient for the rest of the results that I'll be showing later on. But before that, so how do we quantify if a material is a good thermoelectric material or not? And what do I mean by that? Like, if I take a random material, will that be efficient enough to convert heat into electricity? The answer is absolutely not. So the way we quantify it is through this parameter called the thermoelectric figure of merit, which is also denoted by ZT. So ZT is the final value that we'll be calculating. Now, given that we have different people from different backgrounds in the audience, perhaps, I decided to keep the presentation as non-mathematical as possible, and I promise this is the only equation in the entire presentation. I will not show a single other equation. So let's look at the equation. So ZT is equal to S squared sigma T divided by kappa E plus kappa L. S being the Seebeck coefficient, which we already discussed in the previous slide, sigma being the electrical conductivity, T being the absolute temperature, kappa E being the electronic thermal conductivity, and kappa L being the lattice thermal conductivity. Now, we need to keep this in mind. The thermal conductivity can be contributed from by both the electrons as well as the vibrations in a system. Now, when we look at the equation, it seems quite simple. It's not difficult at all. It's like there are no complicated integrals or differentials, etc. It's a very, very simple equation. And if the idea is to increase ZT, because the higher the ZT, That means the more efficient the material is in converting heat into electricity. So in order to increase ZT, just by looking at the equation, looking at the numerator, I can see that, oh, we could increase the S, the sigma, and the T. Or conversely, we can even decrease the kappa E or the kappa L, which is in the denominator. Sounds simple as well, but the problem is that these parameters are not completely independent. They are somewhat coupled. To give you an example, if we increase S, Seebeck coefficient, my sigma tends to decrease. That means I'm not being able to increase both of them simultaneously. At the same time, if I'm increasing sigma, my kappa E also increases, because sigma and kappa E are related by something called the Weidmann-Franz law. So, and kappa E is something that we want to be low. We don't want the denominator to be large in value. Now, somebody can tell me that, oh yeah, okay, sure, but what about the temperature? We can increase the temperature as much as we want to. Yeah, sure, we can do that. But ideally, I would not want to run a device at 1000 degrees Celsius. I would want to run the device at 300 Kelvin at room temperature. So we can see that with regards to the Seebeck coefficient S, the electrical conductivity sigma, the absolute temperature T, and the electronic thermal conductivity, that is kappa E, we can't do much about it. The only remaining parameter with which we can play quite a bit is kappa L, the lattice thermal conductivity. And that's what will form the crux of this talk. Okay? This is a little bit of a historical perspective. You can see that from the 1940s itself, there's been a lot of effort in improving, or rather increasing, the ZT, the thermoelectric figure of merit. From the 1970s till the 1990s, it hit a plateau. But then something happened in the early 90s, after which the ZT value once again shot up after a hiatus of like 2 or 3 decades. If you look at the diagram in the early 90s, you'll see this little arrow, and it mentions Higgs and Dresselhaus. So something probably happened. And what happened was Mildred Dresselhaus, this absolutely phenomenal physicist who specialized in thermal conductivity and thermoelectric materials, she came up with this phenomenal theory, which we'll discuss in the next slide. And that theory was proven to be true. And that revolutionized the field of thermoelectrics completely. Right. So the story goes, like in the early 90s, Mildred Dresselhaus was approached by the US Navy as well as the French Navy to come up with a method to improve the thermoelectric performance of materials. What she proposed was that if we decrease the dimensions, the physical dimension of a system, then the thermal conductivity will probably decrease, as a result of which the thermoelectric figure of merit will probably increase. This was tested out theoretically initially, and she saw that when we went from the 3D regime to 2D regime, indeed, that was what was observed, like the ZT increased quite a bit. When they went from 2D to 1D, it increased even more. And why does that happen? It happens because of this concept called boundary scattering, which I will not discuss in detail, but I will touch upon later in our slides. But when we scale down from higher dimensions to lower dimensions, the boundary scattering effect increases, which eventually decreases the lattice thermal conductivity. And keep this in mind from the previous slide, that the lattice thermal conductivity, the kappa L, was in the denominator of that one equation that I showed. That means in order to increase ZT, I need to make my kappa L, or the lattice thermal conductivity, as low as possible. Okay? Needless to say, what happened was in the late 90s and in the 2000s, there was a huge amount of research done on 2D materials with regards to thermal conductivity as well as thermoelectric effect. So I'll just give you a few examples, like maybe 3 examples. of 2D materials and their thermoelectric properties, and then I'll move on to my own project. So the first one, graphene, the quintessential 2D material. But unfortunately, graphene has a very high thermal conductivity and very low Seebeck coefficient, because of which the ZT turned out to be quite low, and was in fact lesser than 0.02 at room temperature. So it was not something great. People moved on, and eventually they came up with this other family of materials, or the 2D chalcogenides. Here I've just given the example of 2D indium selenide as a potential thermoelectric material. Many different materials have been studied, like Bi2T3, Bi2Se3, indium sulfide, gallium sulfide, whatnot. And they saw that, at least theoretically, they were able to predict ZT values which were much higher than that of graphene, by the way. Okay. One more example would be another 2D chalcogenide, but this time it was tin chalcogenide. Tin telluride, tin selenide, tin sulfide. It was a theoretical paper, but nevertheless, they found, you can see that the SNTE, the purple bar, reached a value of ZT value of almost 4. Now, this is huge, and albeit that in theory, these values could be quite overestimated. If we did this in experiment, probably these values would become much lesser, but it would still be quite high. So this was quite promising. Now, taking cue from these previous studies, we came up with an idea as well, how to further advance this field. But before I go on to the material that we studied, it's absolutely quintessential that we talk about how can we achieve low lattice thermal conductivity. So quite a few years ago, 5 decades in fact back, SLAC came up with 4 different criteria for achieving low lattice thermal conductivity. The first one being that the whole system should have high average atomic mass. The second being weak interatomic bonding. The third being high phonon scattering. And the last one being high anharmonicity. Now, what we'll do is we have to keep this in mind. And in all the later slides, I will actually keep on showing these 4 criteria and if we are satisfying them or not. If these 4 criteria are satisfied, there's a very high chance that we will be able to predict very low thermal conductivity for a material. Okay. The last slide before I start discussing my material is the methods in which we actually did all these calculations. The geometrical relaxations and the optimizations were done using VASP. The second order force constants and the phonons were calculated using phonopy. The third order force constants and the lattice thermal conductivity were calculated using Cheng BTE. This is a Boltzmann transport equation solver. And finally, the electrical transport properties like the Seebeck coefficient, the electrical conductivity, and the electronic thermal conductivity, they were all calculated using this code called Bootstrap. So it was a combination of quite a few codes that we used, which gave us the final results. Right, so this is where we start. The family of materials that we studied was basically the group 13 chalcogenides. I'll explain. We'll actually spend some time on this slide now. If you look at the structure on the top layer, you will see that they look identical, AX1 and AX2. But they look identical from the top view, hexagonal structure. There's absolutely no difference. But if we look at them from the side view, that is the lower row, we see that shape-wise and space group-wise, it remains same. But there's a very subtle difference. The difference is that in AX1, the group 13 elements, that is A, gallium, indium, thallium, they occupy the outer planes. there are 4 planes, 1, 2, 3, 4. So they occupy the outer planes, whereas the chalcogens, that is the sulfur, selenium, and tellurium, they occupy the inner planes. In AX2, it's exactly flipped. So here, the chalcogens occupy the outer plane, and the group 13 elements occupy the inner 2 planes. If we go through literature, you'll see that a lot of work has been done on group 13 chalcogenides, experimental, theoretical, all of it. But it has always been done with regards to AX2, because that is the ground state structure. Nothing has been done with regards to AX1, absolutely nothing. So, but then after running a few structural prediction calculations, we saw, and also verifying that from databases of 2D materials, we saw that this structure, that is AX1, also exists, not just exists, but it will also be dynamically, thermodynamically, and mechanically stable. But it will not be the ground state structure, it will not be the minimum energy structure, it will be a metastable structure. Nevertheless, it's also a very interesting structure. And I had my hunches. When I saw this material, we had this hunch that perhaps due to a few hints, maybe we might get a low thermal conductivity. Already for AX2, which has been studied extensively in literature, the thermal conductivity was already quite low. Maybe not very low, but quite low. Compared to graphene, yes, very low. But could we decrease it further in AX1? And this was the structure that we particularly studied and compared with AX2, which has been reported plenty of times in literature. Now, if you remember, the first criterion of SLAC was we need to have high average atomic mass. The reason being that the high average atomic mass would decrease the phonon frequencies, the vibrational frequency, which would indicate that the group velocity will probably decrease, which would probably decrease the lattice thermal conductivity as well. Now we can see that in our system, we have in our systems we have elements like thallium, tellurium, selenium, indium, which are quite heavy. So that means the first criterion is met with. We do have a pretty high average atomic mass. Now the second one was weak interatomic bonding. Why? Because the weaker the interatomic bonding is, the lower will be the elastic constants, which means that, and the thermal conductivity depends on the elastic constants very, very strongly. So if we can get lower elastic constants, that means our thermal conductivity also has a very high chance of being low. So let's look at the diagram on the right. This is called the electron localization function. We can just focus on the middle layer, that is the INX layer. It's all same otherwise. For figure C, we can see that the outer planes are occupied by indium and the inner planes are occupied by chalcogen, X. For figure D, it is exactly the opposite. Indium occupies the inner plane and the chalcogens occupy the outer planes. So basically C corresponds to AX1, the structure that we predicted as well as got from the database and have been exploring. And D represents the AX2 structure, which has already been studied extensively in literature. Now, in an electron localization function plot, the more red it is, that means there are electrons localized in that place. And the more green or blue it is, that means that place doesn't have a lot of electrons. So if I look at D for AX2, you'll see that between the two indium atoms, it's red. That means there's a very strong covalent bond. That means the bonding is very strong. And that is exactly what we don't want. Because SLAC's second criterion was we want weak interatomic bonding. But if we look at AX1, that is figure C, between the two chalcogen atoms in the middle layers, it is green. That means the bonding is quite weak. That is exactly what we want. That means just by looking at this electron localization function plot, I can predict qualitatively that maybe my elastic constants will also be low for the AX1 structure compared to the AX2 structures. Let's check that. And there you go. If you compare the different columns for the same materials, the corresponding materials, you'll see that the Young's modulus, the shear modulus, the Poisson's ratio, the velocities, and the d by temperature, which is very important, the last column, for AX1, they're much lower compared to the values of AX2. Let's take, for example, TLSE. So, or TLTE, the last one. The Young's modulus is only 10.12 for AX1, whereas it's 28.16 for AX2. And you can check for all the values. They will always be much lower compared to AX2. That means my second criterion of slack, weak interatomic bonding, has been satisfied. So we have satisfied the first two criteria. Okay. This slide it depicts electronic properties, the electronic band structure, and I've tabulated the electronic band gaps as well. Doesn't affect our thermal conductivity much, but just by looking at the graphs, we can have a pretty good hunch that just from the band gaps, we can predict that at slightly higher temperatures, we might be able to use these materials as pretty efficient thermoelectric materials. I'll not spend much time on this, but all the calculations were done using both PBE and the hybrid functional HEC06. Okay, now, the dynamical properties or the phonons. So if you remember, the third criterion of slack, which I've written on the bottom right corner again, was we needed high phonon scattering. Here, I have just shown the same thing for two particular materials. I could have shown it for all of them, but this paper had a lot of graphs. So here I've just shown it for indium sulfide and indium selenide. Now, for the AX1, which is indium sulfide 1 and indium selenide 1, we can see that there is more phonon anti-crossing between the acoustic branches and the two lowest optical modes compared to the AX2 structures. It's very difficult to actually see the phonon anti-crossing because it has to be highly magnified to point that out. But we actually saw that there was actually much more phonon anti-crossing in AX1 compared to AX2. And the anti-crossing was happening with the first and second modes, optical modes, with the acoustic modes as well. And we have depicted the optical modes here, if you're interested. Now, what does phonon anti-crossing imply? It means that there will be more scattering. There'll be more phonon hybridization and there'll be more scattering. That's exactly what we were looking for. That means compared to AX2, our structure AX1 has more phonon scattering. So 3 of the criteria have now been fulfilled. Okay. The last criterion was that we need high anharmonicity. So we decided to plot the scattering profiles of all the materials. Here again, I've just shown it for TLSE as a representative, but it's very, very similar for all the other materials too, whether it's indium sulfide, indium selenide, indium telluride, the thallium series, the gallium series, it's basically very similar. And we see that at lower frequencies, at lower frequency vibrations, the anharmonicity is actually very high. Especially if you look at the graph at the bottom, the gamma, that actually represents the Gruneisen parameter, which itself measures the anharmonicity. And you can see that at lower frequencies in the acoustic region and for the first two optical modes, the Gruneisen parameter indeed is extremely high compared to the, when I say high, I mean magnitude-wise high. So it could be negative, it's negative 40, but the magnitude is quite high. Whereas for the higher frequencies, this value hovers around 0. That means for the higher frequencies, this material is not very anharmonic. It's only for the lower frequencies that it's very anharmonic. And values like -40 or -45, these are actually very high numbers for a Gruneisen parameter. That means now all my 4 criteria have been satisfied. So I have high average atomic mass, weak interatomic bonding, high phonon scattering, and high anharmonicity. So just by looking at these graphs, I can predict that maybe the lattice thermal conductivity, kappa L, will be quite low, because that's what our goal is. Moment of truth, and there you go. Indeed, our prediction came true. In fact, it came true too well. If you compare, let's look at the first pair, indium sulfide 1, indium sulfide 2, AX1, AX2. At 100 Kelvin, for AX2, the thermal conductivity was the kappa L, the black line, was 200 watt per meter per Kelvin. The same for AX1 or INS1 was barely more than 1. So it was almost like 150 to 200 times lesser. And you'll see the same trend for all these graphs, whether it's the indium series or the thallium series or even the gallium series, it will always be the same. So that means compared to the AX2 structure, which has been studied extensively, compared to that structure, our structure theoretically gave us extremely low lattice thermal conductivities, which we also call ultra-low lattice thermal conductivity. Because for some of the values, they're actually even lower than 1. And once we increase the temperature, like if we go up to 1000 Kelvin or even 900 Kelvin, we see that they become actually very, very close to 0. It can't be 0, of course, but it's definitely much lower compared to 1. Whereas for the AX2 structures, they're always above 20 or 30, etc. That means that was a huge improvement. And that's exactly what we wanted. So therefore, if we remember the first equation that I had shown you about for ZT, I have successfully predicted a structure for which the kappa L will be very low. But we also have to find out the ZT, because the ultimate aim is to increase the ZT. Okay, let's check that. Here, it's just a confirmation graph where we have shown that the kappa L, the lattice thermal conductivity, is mostly contributed by the first 5 modes. That is the first 3 acoustic modes and the first 2 optical modes, the low frequency optical modes. And after that, it stagnates, it converges, which means that the higher energy, higher frequency optical modes do not contribute to the lattice thermal conductivity much anymore. Okay. Now, as you remember, in that formula for ZT, we also needed the S, which was the Seebeck coefficient. We needed the sigma, which was the electrical conductivity. And we needed the kappa E, which was the electronic thermal conductivity. Again, here I've just shown it for TLTE. This was done for all the structures. I'm just using TLTE as a representative for this slide. And once we have all these numbers, we can plug everything into that one equation, and this is what we get. So you see, for the gallium series, it was not that high, perhaps. But if you look at the indium series, here, the graph on the right, they're actually very high. In fact, if you look at indium selenide, the middle row, for AX1, indium selenide 1, for our structure, compared to indium selenide 2, the ZT value reached values more than 5. That is humongous. That is huge, absolutely. Similarly, for indium sulfide or indium telluride, we got values more than 1, almost close to 2, in fact. But the interesting thing is that for all these systems, we can see that the ZT value for our system, or our systems rather, which is represented in green, is consistently higher and significantly higher compared to that of the AX2 structures already reported in literature. This is the same basically for the thallium series. You can see that again, values reach above 4, 2, 1.5, very, very high values once again. And the same trend is noticed. That is, for our structure, for the AX2 structure, it is always much higher compared to that of the for the AX1 structure, which is our structure, it's always comparatively much higher compared to the AX2 structure. All these results were published, and most of these graphs will be found in the second publication, which was published a year and a half back in Nanoenergy. Now, conclusion from this work is that when we just flipped the atomic positions, in the conventional system, we saw that the group 13 elements occupied the inner planes and the chalcogens occupied the outer planes. But in our system, we just flipped it and we saw that the bonds became much, much weaker. The Debye temperature decreased significantly. The phonon got scattered even more. The anharmonicity increased a lot. Therefore, the lattice thermal conductivity decreased drastically, and as a result of which, the thermoelectric figure of merit increased extremely as well. So, based just on Slack's criteria, we were able to design a material, or we were able to predict the properties of a material, and our predictions came out to be absolutely true. We just wish that they are eventually experimentally verified as well, because this can probably advance the field of thermoelectrics quite a bit. My last slide. So, when we get values of 4 or 5 of ZT, in theory, these values are a little overestimated. Because if we do these same things, the same experiments in a lab with the same material, they will probably come down quite a bit. Like the 4 might become a 2. The 3 might become a 1.5. And the reason is because in theory, when we are doing the computations, we don't take every effect into account. They're very good approximations, though, but we could probably improve the calculations further. And that's what we are currently trying to do. The first one is to consider 4 phonon scattering. Here, we have only considered 3 phonon scattering, but we can also consider 4 phonon scattering, which might be significant for some materials or may not be significant at all. But it's always worth checking. But the calculations become much more complicated and more expensive. Secondly, a very important factor is electron-phonon scattering. And this, if we haven't considered that either. But if we do consider the electron-phonon scattering, the relaxation time might actually change quite a bit. This will significantly affect the results. Thirdly, something that we are currently doing, I'm doing it with some of my colleagues and collaborators, we are comparing the results obtained from DFT, molecular dynamics, and machine learning. And we're trying to figure out which result matches well with those found in experiments, or maybe a combination of different approaches. And lastly, based on Slack's criteria and not based on hit and trial, because if we go through a high throughput methodology, it's kind of like a hit and trial where we keep on filtering. But if we want to use real scientific background and on the basis of the Slack's criteria, we are trying to screen more materials with lower thermal conductivity. And some of these materials would include lower dimensional perovskites. We already know what perovskites are, but perovskites can exist in different dimensions as well. So we're looking for lower dimensional perovskites following Dresselhaus's proposal that if we lower the dimension, the thermal conductivity will decrease. So that's what we are currently doing. And a lot of interesting things going on in this field. A lot of interesting projects I'm actually doing with my collaborators. And that would be it. Thank you very much. Feel free to ask your questions, or if you have more questions later on, feel free to reach out to me by emailing me, or you can even find me on LinkedIn. Thank you very much.
Thank you, Dr. Majumdar, for a very nice presentation. And now I guess we are ready for the QA session, because we have several questions in our chat on the YouTube. I will highlight them one by one, just read them out loud, and then you will have a chance to answer them. Sure. So the first question is, why only binary materials are discussed? And I suppose people mean that on the slide which you showed at the beginning, the only structures which were depicted there were the binaries. And I guess at the very beginning, I guess.
Right. Yeah. So it's a little slow actually. So yeah, I'll find it.
Why don't we take care of other materials which consist of more than 2 atom types?
That's a good question actually. So many of these materials are actually not yet experimentally observed. These are theoretically predicted materials. Now, when we are theoretically predicting materials, firstly, structural prediction itself is quite complicated. There are different approaches. We can use particle swarm, we can use random sampling, we can use basin hopping, we can use genetic algorithm. But it becomes even more complicated when we go on to ternary materials, like 3 elements, or even more difficult when we go on to quaternary materials with 4 elements. So for now, our bandwidth was to kind of, or not just our bandwidth, but most of the people worked with binary materials theoretically because they were computationally less expensive to predict. That's why. But yeah, that's a very good point. And in fact, there have a lot of advancement has taken place in the field of structural prediction. Sorry. And ternary materials are being predicted now. It's just that they take a very long time. So we would be very interested in doing that too, once we have the proper resources.
Thank you, Arnab. And the next question is about the applications. So what is the general necessity in materials with low thermal conductivity? So why do we need them?
Right. So as I mentioned, so so the idea is to increase the thermoelectric figure of merit, the ZT. Because the higher the ZT, that means I'll be able to convert more heat into electricity. And when I'm talking about heat, mostly this is wasted heat, the heat which has been lost. So, but I don't want to waste energy. We all want to use energy as much as possible in a constructive way. So if we need to increase the ZT, or if we need to improve the thermoelectric figure of merit, we need to decrease the kappa L, 100%. So to answer the question, for applications, kappa L, we need low thermal conductivity when we want high-performing thermoelectric materials.
Thank you, Arnab. I think now it's more clear why do we need them. And the next question is rather theoretical. So why should the photon scattering should be low according to these slack rules that you mentioned?
It should be high, actually.
Should be high. Yeah, probably the person just mistyped. Yeah, should be high. Why is it so?
Checking if I mistyped that. Yeah, it should be high. So because of the scattering channels. So if we have more scattering, the heat is not getting a lot of channels to dissipate. Because in order for the heat to get dissipated, we need a lot of channels or pathways. But when we have too much of scattering, these channels are getting blocked, and hence the heat is not being able to dissipate. So that's why we eventually end up having low thermal conductivity. And conversely, if we want a material with high thermal conductivity, then we want low phonon scattering, actually.
Thank you. And the next question is from Trifon Ivanov. So I will cite it. Dr. Arnab, thanks a lot for the kind lecture. I have the following question. I didn't understand why we need high anharmonicity for materials with high performance thermoelectric properties.
So the high anharmonicity part is related to the thermal conductivity. So it's kind of indirectly related to the thermoelectric efficiency. But for example, I'll give you an example. For instance, let's say diamond. Diamond has very low anharmonicity. It's a very, very strongly bonded material with extremely high harmonic characteristics. and it has a very low anharmonicity. Because of that, the thermal conductivity of diamond is also very high. So now, the anharmonicity depends on many other factors as well. So just to give like an overview, for example, when you don't have very strong bonds, or when you tend to have lone pairs in the elements, these lead to rattling. And the more it leads to rattling, what's happening, we are coming out of the harmonic regime eventually. And this anharmonicity opens up a few more scattering channels, therefore. And that's why we need the high anharmonicity so that we get lower thermal conductivity.
Thank you. And the next question is, have you tried to verify your calculations by experiments?
No, actually not. So in fact, most of these predicted structures are not experimentally verified for several reasons. One is that experimentally, it's still a little challenging to discover 2D material, freestanding 2D materials. We have found 2D materials on substrates, but for freestanding, it's actually quite difficult. But then again, a lot of the 2D materials have been discovered on substrates as well, and they have been studied extensively. But this material, no, we haven't, and that's why in my last slide I mentioned this. I hope somebody takes up this project and does it experimentally as well.
We hope that this presentation on our YouTube channel will make your work popular, and probably some other research groups will see it and decide to synthesize all those materials which you mentioned. The next question is, will this approach work for any layered structure?
Very good question, actually. So ideally, yes, probably. And the reason is because the proposition made by Mildred Dresselhaus that when we lower the dimensions, what's happening, we are increasing the boundary scattering, which impacts the thermal conductivity. And again, like as I mentioned, that the scattering has to be high. So if we are adding one extra layer of scattering, which is boundary scattering, which happens in 3D materials as well, but it's obviously much lower. But in 2D materials or 1D materials, the scattering increases. So when we have layered materials, what's happening, again, there'll be a lot of scattering because we have more boundaries. Let's say we have a material with 4 layers. So it means there'll be 4 different boundaries, and yes, there'll be more scattering. So ideally, yes, this method should work for layered structures as well. That's a very good question, actually.
So let's move on further. And the next question is, what is the relation between the size of nanostructures and the phonon scattering?
I didn't get the question.
I have actually cited it. Mangaladip Halar. I hope I pronounced your name and surname correctly. Sorry for mispronunciation.
Can you repeat the question once more?
So probably you can reformulate your question, and in the meanwhile, I will ask my own question because it was the last one in the list. Okay. The question from me is the following. So you have mentioned the functional which you used to predict the structures and probably optimize them and so on. Have you tried, so what was the procedure to choose this functional, this specific one? And the next question is, have you tried some others? And if yes, have you confirmed the results which you obtained with this functional?
Right. No, we haven't tried any other functionals. The reason that we chose this one is because the PBE is the most standard one, and for the electronic properties like the band gap or the density of states or the electron localization functions, we did hybrid functional because they predict the electronic properties better. But we chose PBE mostly because it's a very standard one. But we did not verify it with other functionals, no.
I guess it might be interesting to test the others.
Probably.
It will have some impact, and you have mentioned that you want to compare the results with other methods. So the question from Mangla Color is the following. What is the relation between the size of nanostructures and the phonon scattering based on the thermal conductivity?
Well, so I think that's related to the high phonon scattering again. So for instance, experimentally it was seen that when we are decreasing the dimensions more and more, let's say from 15 nanometers to 10 nanometers to 5 nanometers, etc., or maybe 8 nanometers, the thermal conductivity kept on decreasing, which meant that the boundary scattering kept on increasing even more. Because that is the main term which will affect the thermal conductivity with as a function of the dimension or the system size at the nanoscale. So it's a boundary scattering which will increase. The phonons will basically scatter off the boundaries more, and that will lead to lower thermal conductivity because even lesser channels will now be available for the heat to get dissipated.
Thank you for the answer. And here comes another question. Does the photon scattering affect the lattice thermal conductivity and the size of the nanostructure?
It affects the lattice thermal conductivity for sure. As I mentioned, like the higher the phonon scattering, the lower the lattice thermal conductivity, and vice versa. But it does not affect the size of the material because the size of the material is the basis, is the fundamental information based on which we are doing the calculations. So no, the phonon scattering will not affect the size of the system. It's in fact the opposite. The size of the system will affect the phonon scattering.
Thank you very much for the presentation. I guess we approached the end of our presentation because there are no more questions in the chat. Thank you, Dr. Majumdar, for coming. It was a pleasure to host the talk with you. And everybody who watched this presentation are welcome to register on the website and apply for their own presentation on our YouTube channel.
Thank you very much for inviting, by the way. This was excellent. I had a really wonderful time presenting these results. And for more details, definitely refer to the paper that I showed in the last slide, the nanoenergy paper. That is, in fact, a huge paper. That paper actually has 200 graphs. And it's not a review paper. It's a proper normal paper. So it was a very, very big paper, very detailed. So definitely refer to it if you're interested.
Thank you very much and see you.